Regards from Niš and from the Center of Applied Mathematics of Faculty of Mechanical Engineering. We apologize for a delay. We have here our television, and it is maybe a time finally to start the opening ceremony of our conference. I'm invite Academician Mahouton Norbert M.N.Hounkonnou to chair the opening ceremony part of our conference.
Thank you, Professor M.Mitrović. Distinguished guests, scientists, young researchers. So, the Academician Vladimir Rakošević, corresponding member of the Serbian Academy of Science and Arts. The Academician M.N.Hounkonnou, member of the Academy of Science and Arts of Bosnia and Herzegovina. The Vice Dean of the Faculty of Mechanical Engineering, University of Niš, Serbia, Professor Predrag Janković. The Dean of the Faculty of Economics, University of Belgrade, Serbia. The incoming Vice Rector for Science, Professor Branislav Borisic. The Head of Institute for Education, Quality and Evaluation, Belgrade, Professor Branislav Randelović. The Head of the Center of Applied Mathematics of the Faculty of Mechanical Engineering, University of Niš, Professor Melanija Mitrović. Chairs of international colloquiums for this conference, the members of the program committee, the members of the local organizing committee, all other protocols observed. I'm truly honored to be part of this distinguished gathering of top-level scientists and eminent persons, and to have the pleasure to address them some welcome remarks on behalf of the international organizing and program committee members. First of all, allow me to express our gratitude to individuals who have worked tirelessly towards the preparation of this great conference held to foster excellence in science through knowledge sharing in semigroups, algebraic structures, and their applications. Your efforts put the conference series, Algebras Without Borders, on the global stage of advancing utilization of algebraic structures in all life sectors. The path towards this year conference started from our meeting at a conference organized by Professor Sergei Silvestrov in 2019 in Sweden, where Professor Melanija Mitrović and myself discussed and developed a plan for a series of conferences on algebras without borders. The first edition of this series was scheduled for August 2020, but was unfortunately postponed to these dates of September 2021 due to the harmful COVID-19 pandemic. In the meantime, we organized a webinar on mathematics for human flourishing in the time of COVID-19 and post-COVID-19 on 21st of October 2020. Again, also an international multi-continental conference on mathematics for social sciences and arts, algebraic modeling, from 24 to 26 of May 2021, in collaboration with Professor Filipa Pattiston from Australia and Professor Dragana Martinović from Canada, and an international conference on classical and constructive non-associative algebraic structures, foundation and applications, from 30 of June to 2nd of July 2021, in collaboration with Professor Murahid Abbas and Professor Madad Khan from Pakistan. This 2021 edition of the first of this series developed such important topics as classical and constructive semigroups and applications, focusing in their strengths and recent developments. In addition to a general session dedicated to semigroup theory with classical and or intuitionistic logic as background, which will go on in the first part of every conference day, the conference comprises a set of main colloquiums shared by leading field scientists to help shed light at ways in which these theories have been developing, understanding, and applying in various domains. The general sessions and the colloquiums will focus on recent development in semigroups and other basic algebraic structures, as well as on some of their potential applications in other fields. There will also be an opportunity for participants to present short talks. Looking at these rich programs split in 3 days, we will have fruitful discussions and enjoy our conference. You then will understand why I want to express our gratitude to all people who are supporting us in this new adventure that gives a response to the requirements of interdisciplinarity and necessary dialogue and marriage of all algebraic structures to face contemporary global changes. I therefore, on behalf of the program committee members, would like to thank the Dean and all his staff of the Faculty of Mechanical Engineering of the University of Niš and other anonymous persons for their accompaniment and support through this conference towards their effective presence at the opening session. Finally, allow me to reiterate first and foremost the value of having this first edition in Niš, even virtually. A so beautiful city, a historical city full of emotions, majesty, and grandeur, a gauge of a successful conference. We are very happy to be here, at least virtually, being unable to attend physically this scientific meeting and to live and appreciate the cultural and historical wealth of your great city. This is only a postponement. Thank you very much for your attention. Now, let me invite the Vice Dean of the Faculty of Mechanical Engineering, University of Niš, Serbia, Professor Predrag Janković, to address some words to the assistants. Dear Professor, please take the floor.
Professor. Welcome once again to everyone. My name is Predrag Janković, and dear colleagues, dear guests, allow me on behalf of Dean of Faculty of Mechanical Engineering in Niš to greet you and wish you a successful work on our conference. I wish to present our faculty in short presentation. Just a moment, please. Our faculty was established as a part of technical faculty, and from 1971, our faculty is independent institution. It is part of University of Niš, which consists 14 faculties. Currently, we are having 97 professors and teaching assistants, 8 expert associates, and 45 non-teaching workers. What is important is our study programs. We have 2 study programs, mechanical engineering and engineering management. For mechanical engineering, we have all 3 levels of studies, Academician studies, master studies, and doctoral studies. On engineering management, we have academic and master basic and academic, bachelor and master academic studies. In last academic year, over 200 students are graduated on academic studies, and also just over 200 on master academic studies. Currently, we have over 1,500 students on our faculty on all three levels. Our institution, besides of education, is dealing with scientific research and also cooperation with commerce, with industry. From international level, our professors and associates work on numerous projects. Also, we are dealing on over 20 national projects financed by National Ministry of Science. Also, these results are presented besides of international journals on many conferences like this one, and these are conferences held in only in this year, which was difficult, like past one, but we, as Professor Norbert said, we are trying to keep the pace, even virtually, but we all hope to better times. And that will be all. Thank you for your attention. I'm calling now Professor Melanija. Yeah, Professor Norbert, please, Professor Norbert, go on with opening ceremony.
Thank you, Professor Jankovic. Now I would like to invite the Dean of the Faculty of Economics, University of Belgrade, who will be the Vice Rector for Science from the 1st of October, Professor Branislav Borisic.
Thank
Please,
you.
Professor.
Thank you. Do you hear me?
Yeah, we are hearing you.
Okay. Dear participants of the International Conference on Classical and Constructive Semigroups and Applications 2021, dear keynote speakers, and finally, dear Professor M.N.Hounkonnou and Professor Mahouton Norbert Hounkonnou, spiritus movens of this conference. It is an honor and pleasure to welcome you on behalf of the program committee of this conference and on behalf of Serbia's algebra and logic community, as well as personally on behalf of Faculty of Economics, University of Belgrade, an institution with the longest tradition in Serbia in field of economic science, and I would say an institution where applied mathematics and quantitative analysis are always highly valued and respected. Application of mathematical methods in the field of social and other sciences presents a wider social interest, because I believe that it is impossible to develop serious research and draw valid conclusions without quantitative analysis. Today, I take this opportunity to express my gratitude to all participants and members of organizing committee, staff of Faculty of Mechanical Engineering, University of Niš, for your contributions. And I wish you a lot of success at this conference. Thank you very much.
Thank you, Professor Borisic. Now let's invite the head of Institute for Education, Quality and Evaluation, Professor Branislav Randelović, to take the floor.
Thank you, Norbert. Dear colleagues, dear friends, as a university teacher and member of organizing committee, I'm really glad to welcoming you now, especially the people who managed to come to Niš, and I wish pleasant stay. Who is virtual, I wish him pleasant virtual stay in Niš during this conference. And as a head of institute, who is on behalf of Ministry of Education of Republic of Serbia, responsible for quality of education, I would like to share with you my thoughts that our common job during these 3 days of conference is not just a science, it is something that should reflect to our work with students, and in some second or third round to have a good impact to quality of education in our educational systems. So thank you for this time for giving me opportunity to address you, and I wish you a successful conference.
Thank you, Professor. So we are ending in such a way our opening ceremony, and we will start in a few minutes the general session. Now we start the colloquium on application of semigroups within cognitive sciences and linguistics. This colloquium will be chaired by Professor Marcel Danesi. Professor Marcel Danesi is Professor of Anthropology and Semiotics at the University of Toronto. He has published extensively in math education and psychology of mathematics. He has founded several book series in the field, including Mind in Mathematics with Springer. Professor, please.
Thank you very much. Thank you. And thank you for having me at this marvelous meeting of minds. I should say that my own paper and a little bit of my own section, or the section that I was able to organize with very distinguished scholars, falls a little bit outside semigroup theory. But the whole idea was way back in about 20 years ago, certainly 15 years ago, was to found at the University of Toronto, together with the Fields Institute for Research in Mathematical Sciences, to bring mathematics within cognitive science. And that will be my claim this morning. It'll be a generic claim. Not that mathematics is not studied by cognitive scientists, but my claim will be is why not make mathematics itself part of cognitive science, part of the amalgam of sciences. Now, mathematicians, when they do mathematics, are not necessarily self-analyzing themselves. They leave it for others. My claim will be is don't leave it to others. Let's do it together ourselves. So that will be the main claim. So I will be a generic paper. Please bear with me, humor me if you're a mathematician. But I think I hope to make the case, at least for cognitive scientists, that we need mathematicians, not psychologists only, linguists only, and others, but mathematicians as well as part of this consortium of scholars. Okay. I'm going to be reading askance because I'm not very technical, so I have my paper on another computer. So if you see me looking to this side, I'm reading from my computer, from my other computer. In the mid-1950s, psychologists started adopting insights and terms from artificial intelligence, seeking parallels between the functions of the human brain and those of the computer. By the latter part of the 1960s, this approach became widespread. One of the early promoters of this approach, a psychologist named Ulrich Neisser, put it as follows. He said this: the task of the psychologist in trying to understand human cognition is analogous to that of someone trying to discover how a computer has been programmed. In particular, if the program seems to store and reuse information, they would like to know by what routines or procedures this is done. In other words, the psychologist wants to understand its utilization, not its incarnation. This was radical, by the way, at the time. People have claimed since then that it's Cartesian, that Descartes promoted it. No, he did not. The idea of using mechanical devices and as analogs of cognition might be traced back to Thomas Hobbes, maybe Leibniz, but certainly not to Descartes. Anyhow, Neisser realized that the computer metaphor, if brought to an extreme, would actually lead psychology astray. So only a few pages later, he issued the following caveat, and I quote, "Unlike people, artificially intelligent programs tend to be single-minded, undistractable, and unemotional," which is, of course, sometimes considered, especially today, something perhaps desirable. And so he goes on to say, none of the artificial system does even remote justice to the complexity of mental processes. By the end of the 1970s, psychologists had started to form a partnership with not only computer scientists, but also with linguists of a certain persuasion, mainly those in the field of generative linguistics, started by Noam Chomsky in the late 1950s, developed through the 1960s, and it became a mainstream approach in linguistics in the 1970s. So the linguists of that persuasion or of that ilk, together with psychologists who were using more and more computer ideas as filters, as lenses, as words, basically, to construct and drive their research, a new discipline arose, and it was called cognitive science. Interesting term. I'm going to use a bit of an anecdote. When it did come into being, I was a young professor, becoming much engaged in this sort of stuff. And I became a good friend with Thomas Sebiok, a major figure in semiotics in that era and ever since. And when cognitive science came to the forefront, he said to me, you know what? Cognitive science is semiotics with money. Why? Because the term cognitive science rings well with especially Western thinking. The term semiotic, you know, it's abstruse, it's philosophical, and so on. To downplay this this image, cognitive sciences, then I was there at the University of Toronto. I actually helped establish the cognitive science program at the University of Toronto. They brought in philosophers, anthropologists to say, well, we are a fully developed field, but that was not necessarily true, because their whole idea from the outset was that, as Howard Gardner said it in 1985, that there exists a level of analysis wholly separate from the biological or neurological on the one hand, and the sociological or cultural on the other, and that central to any understanding of the human mind is the electronic computer. However, as in any movement and in any paradigm, splinters start to occur as people do research on the human mind. La fantasia starts to go here, there, and everywhere. And by the 1990s, a movement started to emerge called embodied cognitive science. In other words, to go counter to this idea that the analysis is separate from biology and culture, it is part of it. And it became a major movement, continues on to this day, and it is within the embodied cognitive science movement that I believe mathematics belongs, especially after 1994, a book by Antonio Damasio, a neuroscientist, named Descartes' Error. He refers to the fact that separating the body and the mind leads us astray because you cannot be without it. Now, that's interesting because I'll come back to that a little bit later. The idea that the body and mind were interactive agents, not separate, goes actually back to antiquity. And in the 20th century, it was promoted primarily at first by literary scholars such as I.A. Richards and a philosopher, Max Black. And you can see how a humanistic approach to the mind, together with a scientific, is already coalescing in the landscape of ideas. But Max Black's famous book, 1962 book, Models and Metaphors, I think sets the stage, which for later for embodied cognition, as does a book by two biologists, Umberto Maturana and Francisco Varela, and their 1973 book called Autopoiesis, sorry for the pronunciation, and Cognition, who observed that organisms self-organize themselves according to the input they receive from the environment. So autopoietic systems are often contrasted to allopoietic ones, and those are computer programs. The difference is this: an autopoietic system, such as the human mind, is continuously generates and specifies its own organization through its operations. So ideas emerge from this. Whereas in an allopoietic system, it functions from something different from itself, but its outputs are predetermined. Now, this movement came to a head in 2000, when, for the first time, two embodied cognitive scientists, a linguist and a philosopher, and a cognitive scientist, George Lakoff and Rafael Nunez, published a highly influential book, Where Mathematics Comes From, How the Embodied Mind Brings Mathematics into Being. When it came out, I received an early copy, and I said, this is extremely important. Very predictably, it got two types of reviews: 5-star, wonderful, or 1-star, garbage. The truth, in my view, to this day, is somewhere in between, because it connected language and mathematics via what? You see, people made many parallelisms in the past, but this book connected it through a mechanism, through a process, metaphor. That was close to my heart. I myself became fascinated by the philosophy of an Italian 18th century Italian philosopher named Giambattista Vico, who based his whole view of how the human mind generates rationality through metaphorical poetic thinking. So I said, wow. I actually called up Lakoff, and since then became a good friend of his. He became part of our institute, telling him, but did you know that Giambattista Vico had already thought this out? At first he said, dismissed it. However, one of his students actually wrote a thesis on the idea of what is called pragmatic etymology, which I'll come to in a minute. Now, this book led subsequently to a systematic study of the connection between mathematics, language, and metaphor. Now, if you take metaphor as a process, not just as a linguistic one, but as a process which blends domains of thought into an amalgam, then you have a new field, which, well, you could call, for the lack of a better word, cognitive mathematics. I know this sounds a little clever, but I believe it's a field that is emerging. And in fact, I was able to convince Springer to put out a handbook in cognitive mathematics, which the other speakers in this part in our session are authors in it, to bring mathematics and cognitive scientists together, do their things, and let others figure out what to glean from this. So it'll be out in a, sorry for this is not just PR on my part, trying to promote it. I really do believe that it's the idea that cognitive science may itself be moving towards cognitive mathematics. Now, the distinguishing feature of such an approach and here's where algebra also comes in, is what Aristotle called hermeneutics, interpreting. If you look at early mathematics, and if you look at Diophantus's Arithmetica, where probably algebra starts, he did not just say, well, this is fun to do, I'm abstracting. I want to interpret numbers at a level of abstraction so that I can understand the numbers and that abstraction itself. The claim was not specific, but it was certainly implicit there. So what you have already from antiquity, that mathematics is a hermeneutic science, not just a practical one, it is, not just a theoretical one, it is, but it is also hermeneutic. It tries to explain things through the mathematical code. I mean, it was never labeled as such, but it has always been there in the history of mathematics. Let me quote Immanuel Kant in 1798. While discussing the nature of mathematics, he characterized it as the process of combining and comparing given concepts of magnitudes which are clear and certain with a view to establishing what can be inferred from them. Ring a bell? That's the beginning to me of group theory, certainly a field theory right there. It's in its essence. He goes on to say that, however, you cannot just think about it. You need some way of representing it, expressing it with, his word, visible signs. Well, that's music to my ears, because that's the only way to understand things, to use visible signs, symbols that themselves compress so much information that it takes the mind later to unpack that information in it. So a banal example, what Kant may have meant by this, a diagram of a triangle compared to a diagram of a square will show how they differ visibly. Now you might say, well, that's banal, but no, it is not if you're a child. Especially the connection, if it is made, and as soon as you give a word to it, this is a triangle and this is a square, then the word triangle and square are abstracted and become part of cognition rather than just visible cues to differences. And in fact, the whole of semiotics is based on this, well, a part of semiotics, which one of the founders, the Swiss linguist Ferdinand de Saussure, in the 19th century called différence, minuscule differences. So grasping what makes a triangle not a square is an example of how différence works. So nothing exists in the absolute. Everything exists relative to everything else. Can I give you a banal example of a famous puzzle from the well-known medieval scholar Alcuin in his Propositiones Attaquendus Juvinem. Bear with me, it's a well-known puzzle, but I will need it to make a point. It's the puzzle of the traveler who comes to a riverbank with a goat, a wolf, and a head of cabbage, must go over the bank, finds a boat there that can only hold himself and one other. And he knows that the only way to get across is to make sure that on either side, he does not leave the wolf alone with the goat, who would eat the goat, or the goat alone with the cabbage, who would eat the cabbage. How does he do it? Well, it becomes really a simple solution. He starts with the goat, leaving the wolf and the cabbage alone, goes to the other side, draws off the goat. I'll be quick, comes back, picks up either one, picks up the cabbage, goes over, leaves off the cabbage, comes back with the goat, picks up the wolf, brings them back to the other side with the cabbage, safely goes back, picks up the goat, comes back and goes forward. Now you say, well, big deal. Well, I remember presenting this in one of my classes, and one of the students says, we use this in computer science to understand critical path theory. Well, this is the late 700s. It's already there, the idea. It's what in Latin will be saying, in nuce, in a nutshell, it's there. It needs to be unpacked. So it seems like a natural, common sense one rather than a contrived one. And why is this so? Well, probably because it was sparked by an actual experience, and we all have that experience. Charles Peirce, another founder of SEMIGROUPS, called this logica utens, a practical logic. We all know about this. So at this level, at the experience, it's a logica utens, you know, getting items and animals across the river so that it's advantageous and to avoid possible dangers. But then this situation, when solved, suggests a hypothesis. Then logica utens becomes logica docens, a learned logic, a logic that says, now I'm trying to understand what was intuitive. And that's where hypothesis or hypotheses come into being. And that's what said, what would happen if the traveler had a limited seating boat and things and animals to carry across safely? This then was formulated as a problem, and once solved, we gain an insight that may lead, and has in this case, to an abstract principle of structure, critical path theory. So the notion of hypothesis is crucial to understanding how abstraction operates, which is really part of logica docens. And then we teach logic. We don't teach logica utens, we assume it. Now, even Socrates understood this when he was trying to extract from people by questioning and answers, by the dialectic, how to get people to use their logica utens to arrive at logica docens. In other words, I'm going to pick it up a little bit here. Problems such as this one take the particular and transform it into the general. So far, so good. Nothing new, but it was new then. And that's the point that we become a little bit too sophisticated and a little bit too insouciant as we progress, saying, of course, not when it starts. It's when we discover something anew and retrieve it that true understanding of ourselves occurs. How much time? I'm running out of time? No, I'm okay.
You are the chair.
Okay, I'll speed up. As they say in Italian, scusate molto. Okay, what Charles Peirce called this, when we go from practical knowledge to theoretical knowledge, he used that information. It's not a deduction. Nah, deduction uses it to come to something else. It's not an induction. He called it an abduction, which is a fascinating term. In other words, you take something from over here, bring it over there to create something anew. That became the basis in embodied cognitive science for what they call now blending theory. Rather, when you abduct, and what Peirce also intimated at, and which Lakoff and Nunez did in their book, I think, marvelous process, is achieved through the same kind of thinking, metaphorical thinking, associative thinking, that brings about how ideas are formed. I'll get to that in a minute, but I'll skip some of the parts. I can send you this paper for you to put on the website. It's okay. You know, when semioticians write, sometimes they write too much. It's meant as a joke against me. Anyhow, here's the assumption that the semiotician makes, and that perhaps even cognitive linguists, including people who think of metaphor as a process, is that without symbols, without notations, abductions may not occur. That is an hypothesis that I cannot test yet. I've done some work on it, and I will continue to do work on it. But the only place you can look at is education, children, and math education has been showing that what can be called symbol systems have to be learned in order for abstractions to become real rather than intuitive. And one of the first people to really ensconce this into a pre-cognitive science era, who coined the term algebraic linguistics, was Solomon Marcus, as I was talking to with Melanija ahead of time. I had the pleasure of working with him at the Fields Institute, and he became very excited. Unfortunately, he passed away 2 years ago, that he told me algebra itself is a system of cognition that mirrors everything that happens in the mind. He said there are 5 levels, and I'll repeat to you. I took notes on it. And he says, well, how do we go from counting to equation solving and then to theories like Fermat's last theorem? How does this happen? Well, it takes, first of all, ages. So there is a phylogenetic process that is involved. And since then, people like Brian Butterworth, also a member of our institute, and Stephen Dehen have looked at the phylogenetic aspects of it, whereas mathematical teachers do this every day. They look at the ontogenetic aspects of how this emerges. And here's how, according to Solomon Marcus, the first one is the instinctive ability to count. Not everybody has it. Proof, well, everybody in the world does it. So among us. Second, numerical signs to stand for counting. And this is the second order, and every culture on earth has it. What he was trying to tell me, and it's absolutely true, there is no better or worse system of algebra. They're just different, but they're based on common elements. Some cultures, like the Middle East, parts of Africa and China, had developed different systems, but they all came to similar conclusions. And only, how can I say, cultures that became a little privileged a little later on had the ability, how can I say, the social economic means to continue doing it rather than, and I got this from another person who passed away. His name was Reuben Hirsch, who also became a key member of our institute. Anyhow, we're at numerical signs. This can be called, in semiotic terms, the representational order. In other words, when I have a sign for threeness, I do not have to rethink threeness over and over. I've got it, and I can carry it around as an abstraction. This is the level at which, I'll use a common term, counting concepts are semiotized into numerals. The third one is arithmetic. Well, this is the level at which numerals are organized into a code of operations based on counting processes, adding, taking away, comparing, dividing, and so on. Now, algebra comes in after this. Algebra is the 4th order system that has the capacity to generalize the features and patterns of arithmetic by simply representing them with signs, such as letters or symbols of various sorts. Now, this may seem like banal, but it is not, because then he said, this is where things like groups and group theories come into being. You need that first before the next part comes in. And he called this a meta language. I actually wrote a paper on it much later on algebra as a meta language. But then comes, as I said, semi-group theory, which is a meta language of the meta language. It tries to keep on extracting from the language before, compressing more and more information symbolically and therefore conceptually. It becomes, therefore, in my view, and I had been reading, I'm not that sophisticated in mathematics. So for this conference, I've been reading an awful lot on group theory and semi-group theory. Boy, is it difficult for me. So I've had to use a bit of a template. I called up a few people to help me out and so on. But I get from this that this is the DNA of mathematical thinking. It's at its core of it. It is the 5th order of abstraction. And I should say that linguists have always looked for that as well. Noam Chomsky has searched for the structure of a meta language of grammar, which seems to coincide an awful lot with the meta-meta language of mathematics. So far, so good. But why? What is the source of this? Why do we need this? And this is where the idea of meaning, what a word, meaning comes in. You know, I speak Italian, and the word meaning does not really exist as such. Significato, significazione. Well, there's also signification in English. Meaning has so many things built into it, that word, that in 1922, psychologist Charles Ogden and a literary critic, I.A. Richards, wrote a marvelous book called The Meaning of Meaning, which has become a classic one, in my view, a foundational book for cognitive science today. It was Lakoff and Johnson's book that tried to bring meaning into this mix. So, you know, when you teach something very abstract to a student, they'll say, okay, thank you very much. I can now play with it. I can play with a game. I can play with a chessboard. What does it mean? The mathematicians answers with, here's how it is applied. It is meaning, and it has applications. That is logica docens becoming again logica utens. It's like a back and forth process. But what meaning probably is that something we, like an axiom, distill as telling us something about how we think. It's the brain thinking back on itself. Great pleasure. You know, it is satisfying to understand a mathematical theory in itself. It's almost, in fact, many in mathematics have called mathematics an art for this reason. I don't have to go into this. This is a well-known idea. Let me go a little bit further and go back to Peirce, and then I promise I will stop after this. Peirce saw this as extremely important because then he said, okay, let me look at equations. What the heck is what meaning does an equation have? And in many ways, an equation is like a sentence in language. And in fact, I would claim, and I have here on this session, Vitaly Kiryushenko, who's an expert on Peirce. You'll probably laugh at what I'm going to say. I'm going to say it anyhow, that it is an existential graph. It's a graph. Existential for Peirce means something that it's indexical. It points to things that exist in relation to each other. So let's take an equation. Let's take the Pythagorean one. You know, c squared equals a squared plus b squared. In using existential graph theory, it is a visual portrait, again, a visual sign, going back to Immanuel Kant, of the relations among the variables, originally standing for the sides of a right triangle, of course. But being an existential graph, it also tells us that the parts relate to each other in many other ways, other than in terms of the initial triangle referential domain. In other words, it embeds hidden structure, hidden meaning, because for the semiotician, meaning and structure are often coincident. For example, there are many Pythagorean triples into your sets of integers that satisfy the equation. To use the terminology of current embodied cognitive science, the equation compresses more information that is apparent on the surface, information that is unpacked as its meaning is contemplated. This seems like a clever way around the definition of meaning, but it is not. Because everything goes into a loop. I'm not going to go into that when you define a term. It's from the loop, what you extract from it, that meaning occurs. So the goal of the cognitive mathematical scientist is ultimately to interpret the link between a morphism, a symbolic morphism, like an equation, and meaning. And meaning understood in this way. And therefore, how things such as the number 7 is larger than 4 means Lakoff and Nunez in the book called this a perfect example of a metaphorical idea. The idea is numbers are collections of objects of differing sizes. If you buy that and it's a container in your head, then the container guides how you come to the conceptualization of numbers, bigger and smaller. And the container comes from the experience of measuring, counting things in containers on your hand being a container, for example, having fingers and so on. The other one that they deal of is more is up, less is down. I mean, if you think of linear scales, if you look at graphs, when you look at a curve going up, you say that's increase, going down is that way. Now, of course, it's how the graph is organized, but it is the metaphor itself that gives it meaning. It has to be interpreted. If you show that to a child, it means nothing. It has to be explained as such. But then the explanation is understandable because we have that metaphorical formula in our brain. Now, I'm going to go on very quickly and say that there is now a movement called algebraic semiotics, initiated by someone named Joseph Gauguin, who looks at systems in themselves like algebraic semiotics, with the idea that we evaluate morphisms among systems. And some of the rules of algebraic semiotics is that systems such as mathematics and language are function preserving, axiom preserving, level preserving, priority preserving, and on. But still, while we are dealing with the surface structure of things, it does not explain how things occur. Why is it that when I explain the Pythagorean theorem in language, I preserve the meaning? What is it? What does this? I tried to explain group theory to someone in my household who has no knowledge of mathematics. Totally lost this person. Why? Because I didn't understand it myself that much. I kept on thinking about it, writing it, and eventually it clicked. So translation of meaning occurs all the time. A lot of it is subjective, but a lot of it is guided by the codes we already have. One of these codes is language. Now, is this radical, this idea? No, it isn't. There are many enterprises, the Journal of Humanistic Mathematics, for example. But what it seems to me is that people are discussing this, making very interesting parallels, making connections, and then letting it go. My idea here is to make this permanent, to make it part of the embodied cognitive science movement, so that we can have something at hand, along with music, which has many of the same meaning preserving, function preserving, operation preserving functions. Way back with Pythagoras, who saw this, and Kepler, and continue in this kind of, I don't know what to call it, Pythagorean approach to mathematics as a cognitive science, as a hermeneutic cognitive science. After all, when Abel and Galois were contemplating the solutions of polynomial equations, they asked themselves what they meant. Their proof involved an exploration of the mathematical concept of symmetry. In fact, they may have invented it at that point in new ways. So what we had, they said, if it generates a hierarchy of intermediate polynomials, then we have number fields. Wow, that's a metaphor. There's no other way to understand number fields and group theory and even set theory without the idea of containers and objects that are there. Okay, I'm coming to a conclusion. What would, well, one of the things that always upsets me an awful lot is when, you're called a popularizer of mathematics. And therefore, popularizing mathematics, that's nice. Try to make some money, but it's not real mathematics. Oh, yes, it is. The greatest popularizer of mathematics was Pythagoras. Not to mention Euclid, who not only was so excited about creating the first textbook in the Western sense of textbook. There are many others. In Egypt and Africa, there were many others. But in this sense, organized knowledge, well, he wanted to make it understandable to everyone. And in fact, two books, I will quote two books published in the 1940s, one by two mathematicians, Courant and Robbins, What is Mathematics? And another one by Kazner and Newman, Mathematics and the Imagination. These were meant for a general public. Well, they contain all the ideas, in my view, that can be exploited by mathematicians themselves to base their own discoveries of what's coming forth in mathematics. As mathematics becomes more and more part of truly computer science, as the two become really one discipline, it is the time to really bring a more humanistic, an all-engrossing, overarching view of mathematics as a truly embodied cognitive science. So let me quote a literary critic as my final statement. A literary critic, John William Sullivan, in 1925, put it as follows: perhaps mathematics can be defined truly as an art. Why? Because the significance of mathematics resides precisely in the fact that it is an art, informing us of the nature of our own minds, and therefore informs us of how much mathematics depends on our minds. The interaction is perfect. Thank you for listening to me. Okay, since I'm the chair of the session, I will now go on to our next speaker. I will say it's our first speaker, and it is Dan Vilenchik. I kind of made a mistake in writing his name down, but Dan Vilenchik is truly, in my view, one of the leading cognitive mathematicians today. I learned an awful lot by reading his own work, and he's from Ben Gurion University of the Negev, and his title is An Oblivious, I like that term, by the way, Dan, An Oblivious Approach to Machine Translation Quality Estimation.
Okay, thank you, Marcel, for a really fascinating talk. I never had this view of mathematics as from the philosophical side, as someone who studied computer science and mathematics. And now that I heard your talk, I think that this one will maybe give some example of the ideas that you were talking about. So hopefully, to be modest. Okay, so this is a joint work with master's students of mine, Itamar and Makias, and the title, so I'll just go ahead and start. Okay. Okay, so what's translation? I'm sure everybody knows, is the task of translating text from one language to another. And usually it's done by human beings, by experts, linguists, but starting from the 50s, automatic methods for translation appeared. And by now, those methods are mature, and practically all of us use machine translation, either Google Translate or engines like that. And the state of the art, the algorithmic methodology behind it, now the state of the art relies on neural networks for machine translation systems. Google and the others, they all use neural networks to do the task. And this is an ever-evolving, constantly evolving area. But still, there is need to control for quality. So here are some examples of automatic translation of signs into English. So for example, here from a cocktail lounge in Norway, translation from Norwegian to English, right? So probably they were asking ladies to keep their kids nearby or not to have them running in the bar, but it came out a bit funny. Or you can read the other signs. So while machine translation gives us some good approximation of human translation, still we need to control for the quality. We want to be able to estimate also the quality of the translation. So not just carry out the task of machine translation, but also rank if the translation was good or not. So the most straightforward option to perform machine translation quality estimation is by human evaluation. So you take a text let's say, suppose you're fluent both in English and in, I don't know, in French, and you translate a sentence. You want to know if Google Translate is worth anything. You translate a sentence, and then you look at the output and you say, well, it's an okay translation, or you need to edit it a bit, right? So you can ask, how much effort did I invest in editing the output to bring it to a perfect translation? Right, so experts in translation and linguistics can evaluate input-output pairs, but the problem, right, and there are various criteria like fluency, adequacy, accuracy that they all use, but this is not scalable, right? If we have if we want to understand whether machine translation systems is good, or to give a user some score for the translation that he just did, that he used the system, then we cannot rely on human translation, and we need automatic quality evaluation algorithms for machine translation, also for human translation, but specifically for machine translation. Right, so automatic MTQE, machine translation quality estimation, is an algorithm that, given a pair of source target sentences, gives a score how good the translation is. And good is, let's say, in one of many criteria, according to one of many criteria. So probably, if you are in the area, if you heard about machine translation, then BLEU, bilingual evaluation understudy, that's the acronym, introduced by Papineni et al. In 2002, is the golden standard in the area, and it measures how close the output of the machine translation system is to a professional human translation. So it requires references. And let's see an example. So suppose this is, I have, I don't know, Google Translate, and I have I want to compare Google Translate and Microsoft Translate. So I have a sentence in my source language, and each one of them gave me a candidate translation. So that's candidate 1, that's candidate 2, of some sentence that's in another language which I'm not showing you. And now I want to know which one is better, candidate 1 or 2, or just to say, is candidate 1 a good translation? So those are two tasks that BLEU can solve. So it is a guide to action which ensures that the military always obey the commands of the party. So how does BLEU operate? So it requires references. So I have here 3 references. Human translation of the original sentence, and now I want somehow to measure the distance between candidate 1 and the references, candidate 2 and the references. The candidate which is closer to the human references is declared as the winner, and BLEU does it as many other algorithms. So BLEU is one algorithm, but there are by now many other algorithms that operate in a similar fashion. And what they do is they count n-gram precision. So n-gram, 1 gram, we see here 1 gram. 1 gram is just a single word. So I'm counting how many words in candidate 2, for example, appear in either reference. So every time a word appears in the reference, I'm counting 1. So here I have 8 words that appear in the references. The word ensure, for example, does not appear. It appears as insure. It's another word. So I'm not getting a point for that. I'm getting a point for the red highlighted words that appear also in one of the references. And so my n gram, so my 1 gram precision is 8, and then I can count 2 grams. 2 grams are 2 words that appear together. So for example, the activity, right? So I'm looking for here, no, the activity doesn't appear as a 2-word combination. So for the activity, I don't get a point. And I can count 3 grams, 4 grams, and then combine them together to a score, which says, right, so for every candidate, I'm scoring it according to the n-gram distance from the 3 references, and I get the blue score. And then I can say which reference is better, which candidate is better. So that's like 20 years ago, the technology of machine translation, quality estimation. I'm evaluating which translation is better. But this requires references, right? So again, back to the problem of scalability. I need human reference translations, and that's expensive. So how do we proceed if we don't have reference translation? The answer is simple: machine learning, right? Everything today is solved via machine learning. So how does a machine learning pipeline looks like? So we have, for the training part, we have a corpus of source target pairs translated by some machine translation system. So let's say Google Translate. I have many, many pairs, let's say English to Serbian, right? So I have many, many pairs of translation. Each one is scored by human judgment, by human judges. And so I have a very big, large corpus of pairs source target along with a human score for the translation. So some would be good, some would be bad, right? So the idea is not to get perfect translations. I need the entire variety. And then I feed this labeled data set into some supervised machine learning algorithm. I train it. And then when I get this sentence by Google Translate, I feed it as a test. And what do you say? Is it a good translation or not? Out of 10. 2 out of 10? Melanija.
We used to say that we are second largest city in Serbia, and we always quarrel with Novi Sad. So it is niche or Novi Sad in question. So
no, but the translation, not about the facts.
Translation is okay, but
this is from Wikipedia, so I'm sorry. You have to edit the. By the way, I speak Russian, and I was amazed how close Serbian is to Russian. I could understand perfectly everything. So
Slavic languages.
But yeah, but for example, Polish is much further away from Russian than Serbian. So I don't know. It's very, very close. Okay, so then you give so that's a source target sentence pair, which the machine learning hasn't seen, and then based on the training, it gives a score. Now, no human reference, just this training set. Typically, in the literature, you know, in the computational linguistic literature, the train and the test, when an MTQE system is proposed, then you show how you train it and how you test it. Typically, it's on the same distribution. So let's say Google Translate. So here I have many, many pairs translated from English to Serbian or vice versa, but the direction is fixed. And human judgment, and then I get a pair from the same distribution. And it's not surprised that also here state of the art is neural network algorithms. There is a very well-known workshop on machine translation. That's the yearly competition, part of the EMNLP conference. And they have tasks also for machine translation quality, tasks to develop machine translation systems and machine translation quality estimation. So also the algorithm and the control algorithm for the machine translation. And both in machine translation and MTQE, the quality estimation, neural network-based algorithms give the state of the art, the best results. Now, what if we don't have human judgment score? So here we relied both on source target pairs and on human judgment scores. That's a supervised machine learning pipeline. But getting human judgment scores is expensive. You need to ask linguists, right? You cannot just ask anyone. You need access to experts. That's expensive. So a very natural question is, what can you do if you don't have? And then it's an unsupervised MTQE setting. So in the unsupervised MTQE settings, this part goes away. You just have a corpus of source target pairs. And somehow, by magic, you still are able to train an unsupervised machine learning algorithm to evaluate the quality of pairs. Typically, what you do is all kinds of statistical approaches like TF-IDF. So, for example, if in the source sentence I have very rare words, and in the, so let's say here the word district, that translates as okruga. How do you read it? Okay.
Okrug.
Okrug.
Okruga.
So suppose that districts is a very common word in English, but in Serbian, that's a rare word for district, and maybe there's another word which is closer, which is more frequent in use. I don't know. In Russian, they also say oblast. Oblast.
Oblast. But okrug, yes, it is a common okrug.
Common. But let's say, for the example, that this word is a rare word for district. Then you don't need human judgment. You can just say that something's funny in this translation. It doesn't give, this is a very common word, and this is a very rare word. So all kinds of tricks and more complicated methodologies based on neural networks, but you can think of getting along without human judgment. You can think of getting along without human judgment scores, just based on the language, but still you have the sentence comes from the same distribution. So, for example, if this is one corpus that that is like a baseline benchmark for those systems is the European Parliament translation, the session translation, because it's in all languages. But then it's a specific language. So so you need the TF-IDF, the word frequency, in that corpus, because maybe a certain word appears, it's more legal, has a more legal context, and then you're translating legal information, and that makes sense, right? So still you have a very specific distribution of source target pairs. And on them, you have all kinds of counting and statistics, and sometimes even more complicated algorithms that can still do a quality estimation, tell you how good the translation is. And now we come to the oblivious, to our contribution, and we asked, what happens if you don't even have access to anything? So you just get a sentence in the original language, in the source language, a sentence in the target language. You don't know from which distribution it came. You have of course, no human judgment. You just know in general information about the source and the target. You know the source and target languages, but that's it. You don't know from where it came, which translation system generated it, and what's the area. Is it connected to sports or politics, or what then can you do? And we called it oblivious because oblivious in computer science means that you are unaware, that you have very little information. And can you still perform quality estimation? Can you still, is there some universal signal in the language that you can capture, which will let you evaluate in a reasonable way the quality of the translation? And this is an interesting setting because first, for many languages, you don't have a bilingual corpus, right? So you don't have text and its translation. Maybe for European languages, I know, but there are many languages for which you just don't have these nicely aligned pairs that you can use. Even if you don't have human judgment, you still have them. And of course, human judgment is expensive, and also in the unsupervised setting, we talked about it. And also you can think about robustness. So in the unsupervised setting, you still have a corpus, and then the test comes from the same distribution as the training. And you can then ask, okay, what if I use different corpus for training and for testing? Suppose I train on Charles Dickens, and then I test on another, on Pushkin, or I don't know, with translation to Russian and English. How does this affect the scores that I give the translation? So you can think about robustness. And as I said before, from a philosophical point of view, are there universal signals in the language that are enough to understand if a translation is good or not? And you don't need human judgment scores. And you don't, I mean, if you have them, then you can get better and better approximation of human judgment. That's true. But can you still do something, say something intelligent about this problem when you have very little information, just the general information in the language? And the answer is yes. And we suggested an algorithm, which we call oblivious quality estimation. You always need a nice acronym. And the intuition is as follows. So we think of a sentence as a system of interacting particles. So it's some kind of physical intuition. So the words are the particle, and together they interact like atoms, I don't know, in like electrons and protons in an atom. They interact and they generate a sentence. And the sentence can be in some sense stable, cohesive with a clear meaning, or it can fall apart like, I don't know, an unstable atom. So each word induces a force that's a vector. And if you know about word embedding, word to vec, and all those, and on all this NLP technology, natural language processing technology, where words are embedded as vectors in a very specific procedure called word embedding, and there are various algorithms that use it. But at the end, every word is embedded as a vector. You can think about it as a force vector. And this combination of forces together, on the one hand, the words generate a sentence, but also the sentence has a meaning. So you can think of also a vector representing the sentence, the meaning of the sentence. And this will all be very concrete soon. And then we measure the quality of a sentence. We then use it for translation, but we measure the quality of the sentence, or the quality of the interaction between the words by how much they are aligned, the vector of each word, how much they are aligned with the direction of the sentence. So here is, and we call this measure cohesiveness. So let's make it concrete. I just mentioned that this was recently published in a journal called Mathematics. It's an MDPI journal, Q1. So in a second, I'll show the formula, how we compute it, and then you'll understand where mathematics come in play. But for example, I have this, so it's not really a sentence, it's a bag of 5 words. So here I have a sentence composed of 5 words. The cohesiveness is 1, right? All the words are perfectly aligned with the meaning of the sentence. So for this one, I give cohesiveness 1. The words interact perfectly to generate the meaning of the sentence. Here, I have 5 words. They are around the same theme, right? Food and meal. So the cohesiveness, so this is actually how we computed it. I'll show in a moment the algorithm that computes cohesiveness and how we computed it, but here the cohesiveness is smaller, right? Because of course the words interact, they are not the same word, but they have close theme. So the forces, if you think of each word as a force, they are aligned roughly in the same direction. So you have this. So cohesiveness in this case is a number between 0 and 1. 0 is complete nonsense, and 1 some kind of deterministic sentence. And here you have 5 random words, and the cohesiveness is roughly like 1/5, which is, so every word, if you project it, let's say, on the meaning of the sentence, it's like a projection on a random vector. So it's 1/5. And indeed, those are 5 random words. And if you try to make a sentence of them or think how they come in a sentence, they don't, right? It's just random, it's noise. Okay, so how do we compute cohesiveness? And then I'll show how we use it to evaluate quality, back to the problem of quality estimation. And then I'll show some results of evaluation on data sets, and I'll conclude. So the first task to compute cohesiveness, to compute this measure, we embed the words as vectors. So every word, so suppose this is my sentence, the paper is accepted. Every word is embedded as a d-dimensional vector. And as I said, there are algorithms that take words and embed them as vectors, but not like a random vector. The vectors satisfy the property that vectors that are close, the words that are close by in meaning, have vectors whose cosine similarity is closer to 1. Okay, so in that sense, the analogy of forces makes sense. So if words have different random meanings, they would be orthogonal. Orthogonality of vectors translates to words that have absolutely no common grounds, like monster and functory and gym and lake. All those vectors would roughly have an angle of 90 degrees. Here the angle would be much larger, and here the angle is 1. Cosine is 1 because it's the same word. So each word we embed as a vector, and then we stack the words in a matrix. And then we compute the leading right eigenvector of this matrix. So this matrix is D by 5 in that case, or 4 in this case, depending on the number of words in the sentence. So we have, in this case, a 4 by D matrix. And we compute the leading right eigenvector. And we treat this right eigenvector as the direction of the sentence. That's the meaning of the sentence. And again, so this is SVD, singular value decomposition of a matrix. And the leading right eigenvector is the vector, the one-dimensional space that approximates best all those vectors together. So if you need to choose one direction which maximizes the projection of all those vectors on that direction, or maximizes the energy in that direction, that would be the leading right eigenvector. So here is a more mathematical formulation of the leading right eigenvector. So let's call it V1. V1 is the leading right eigenvector of this sentence matrix. And the SVD theorem says that every vector, every row, in our case, every row is a word vector. So every word vector can be written as a linear combination of all the eigenvectors. So this is some number, some scalar. That's the singular value or the square root of the eigenvalue. So that's the singular value times so this is the vector, this is the kth right eigenvector. So every word you can write it as some component in the direction of V1, the direction of the sentence, what we semantically think is the direction of the sentence, plus some error term, okay? And the energy in that direction is sigma 1, the singular eigenvalue. In this case, where you have 5 words that are the same, then the matrix would have 5 rows that are the same, and there is only, the rank is 1, there is only one right eigenvector, and that's this word. And then it's this word hello, the word embedding of the word hello, and then the word hello is exactly V1 and no error term. As you have more words and more diversity between the words, then there is some direction which we think of as the meaning of the sentence plus error term. And we define cohesiveness as the ratio between the energy in the direction of the sentence and the sum of all singular values. So this is very typical in physics. When you think of a physical system, if you want to know how much energy you have in the leading direction, this is the ratio. Right? So if I go back to this example here, this is how those numbers were computed using this formula, sigma 1, the largest singular value divided by the sum of singular values. So that's a number between 0 and 1. So here, that was 1. There is only one eigenvector, one singular value. Here, the words are, as I said, the word embedding, because those words come from the same theme, all the vectors are roughly close by. And also the leading eigenvector would be close to them. And so the energy of those words in the direction of V1 is rather high, almost 0.5. And if you take random words, then the energy in the direction of the leading eigenvector is also a random projection. That's something like 1 over 5, just out of symmetry. Okay, so this is the measure that we give for every sentence. We give a measure of cohesiveness, which, again, just to sum up, it captures how well the words interact together to generate a meaning for the sentence from a physical point of view. And then our algorithm now to compare two sentences, so S and T are sentences in the source and the target language. We embed S, so let's say S is in English, T is in Serbian. We embed S using English word2vec, T using Serbian word2vec word embedding. We compute the cohesiveness of this matrix, of that matrix, and we have some loss function. You can think of the difference squared, some error function that tells you how far the two sentences are in cohesive measure. So if one sentence is really bad, you want the translation to be really bad. If one sentence makes sense, you want the other sentence to make sense. Okay, and this algorithm is oblivious because it uses for every language monolingual corpus on which the word embedding is trained. And we didn't train the word embedding. We took pre-trained word embedding that are trained, for example, for English on Google News, for other non-English languages on Wikipedia text. So they are available online. You can download them and use them, regardless of the text that we are testing. So they are on general text. Okay, so I'm coming to almost an end. So how did we evaluate our approach? So we compared our algorithm both to supervised and unsupervised algorithms. And the score that our algorithm gives to a set, so all those algorithms, to understand what's the quality of your algorithm, you typically compare the correlation between the score that your algorithm gives to a pair and some human judgment score. So in those competitions, the sets that I'm going to show you are all from competitions. And in that competitions, they invest a lot of money and they recruit human judgments to evaluate the translation quality. And they don't give you this information, of course. You submit your algorithm, and then they tell you how well your algorithm correlated with human judgment. And we checked for various source target language pairs. And for that, so this is for one example of results that we got. So here you see the language pairs that we checked for: English, Spanish, English, German, Japanese English, Japanese Chinese, German English, and Russian English. Here is the source. So here there's citation, but this is WMT. That's the leading workshop for machine translation from which we took the data sets. That's the correlation of our algorithm with human judgment. So the larger the correlation, the better the results. And for every such competition, this is what the first place achieved, correlation of the first place, the baseline. And this is the interquartile range of all the competitors. So of course, the first place is always supervised learning, neural network algorithm, this monster that uses huge amount of data to train. So for example, for English Spanish data set, of course, we don't get the same correlations, right? So it's, let's say, 40% worse, our correlation. And this is the baseline, right? But it's still, it's not a complete, I mean, it's in the ballpark. And we use no human judgment, no training set, nothing, right? So this is the result that we get. On the English-German data set, 0.2 compared, so the baseline is 0.4. First place, again, neural networks with a lot of data to train. For more exotic combinations, Japanese English, we see that our result is not so far from the supervised algorithms. And for Japanese Chinese, our algorithm is exactly as the baseline used by the authors of that paper. And the baseline is already a very good supervised learning algorithm. And then there was this very interesting competition, German English, 2 years ago, where we got, I mean, all the results were very bad. I'll say in a second why, but we got the best result. All of them were very, I mean, the performance was poor. And the reason was that the test was on a different distribution than the train. So they gave algorithms data to train coming from one distribution, and then in the test, they used another distribution. So you see how sensitive those algorithms to the difference. That was another competition. Again, in this conference, they had those two tasks. Now, just so there are no oblivious algorithms, but in this competition, in the English-Spanish competition, there was a paper by Moreira and Fogel, and they proposed an unsupervised algorithm. They got 0.4 correlation in this competition. And then they also said they didn't call it oblivious mode, but then now we train our unsupervised algorithm on general text, which is oblivious mode. And then the correlation decreased by half. So we got 0.37, they got 0.4 when using the same distribution, not oblivious. In oblivious mode, they got 0.2, which is much worse than ours. So I think that this says that this cohesiveness measure gives some non-trivial insight to how sentences in different languages correlate. Okay, so to conclude, in this work, we present a new framework for the problem of machine translation quality estimation. So there's the supervised, setting where you have data plus human judgment score, unsupervised where the task is to evaluate the quality, but you don't know what human judges said about the training pairs. And in the oblivious setting, you don't even have pairs to train on. So you have monolingual data, let's say in 2 languages, and that's it. They're not aligned in any way. And we showed that this cohesiveness that comes from physical intuition and models language as vectors and then computes eigenvectors. So there is a lot of mathematics going on beyond it, or mathematical ideas underlying this linguistic problem. Still, we saw that we get reasonable performance considering the very restrictive setting. The algorithm is completely white box, very simple, no thousands of tunable parameters that you cannot reproduce the result. And for future research, first you can replace this somewhat already dated word embedding with BERT, which is state of the art. For word embedding, this should improve our method. I think it's a nice research direction. You can incorporate cohesiveness in other algorithms as an additional feature, or use it for the task of building machine translation systems to improve the quality of translation. And I think that in general, to understand what happens when you limit the access to data, can you still say interesting things? So for example, unsupervised algorithms that don't use human judgment, can you turn them into, switch into oblivious mode? This is this example here in this paper. Now here, when they switched, it crashed, right? The performance was half. But can you think of methods similar to ours, or I don't know, improve our method so that unsupervised algorithm can work also in oblivious mode and give reasonable performance? And this is, thank you for listening. I hope this translation is good.
Yeah, it is.
Okay, thank you.
So thank you. I think I hopefully within the time framework.
Oh, it's a little loose time. It's okay. It was a wonderful paper. Really, machine translation is at the start of artificial intelligence, as you may know, in the 1950s. So it's crucial to bring this into the whole amalgam of ideas. Thank you very much. So the next person is Rodolfo Del Monte, University of Venice, who will speak on from quantitative linguistics to machine learning language processing. Rodolfo.
Okay. So you, I imagine you can hear me and you can also see the PDF. Yeah. So first of all, thanks to the organizers, and also thanks to Marcel, who always looks the same, even though I met him last time 10 years ago. I don't know how he manages. Anyway, and thanks to Dan Vilenchik for his paper.
Wonderful paper.
Which really made me quite happy about it, because even though I don't share the same opinions, it spared me a lot of explanations on, machine translation and similar problems. Anyway, okay, so my perspective, I will use 2 perspectives, in fact, but the first one will be an historical one. So we're not going into many mathematical formula, even though I will quote them, and you will find them in the paper, obviously. And I have a lot of slides, so I'll move over. Moves. So sorry. I'll have to move to full screen. Oh, here we are. So I divided up this sort of history, the way in which mathematics and statistics intrudes into language studies as a whole, not only language processing, into two main periods. The first period that you see there, where the basic elements are word frequency, corpora, word relation to the context in the structures, the so-called collocates, which will become very important in the future, and then the use of engrams, which already started. As you see there, the period is from the 50s to the 90s, and the Markov chains. The second period, which moves, you know, the way in which the perspective, you know, the paradigm from words to vectors and from sequences to layers, and then back to sequences, because since Dan was quoting the latest BERT algorithm, you know, that is being used, the BERT system is no longer layers in that sense. It's something different. Anyway, here probability has come in, and the Bayesian perspectives, then vector space representation, matrices and tensors, and then finally neural networks. So what happened at the beginning was, you know, there's a number of people like Viff, Herden, Hibbs, perhaps you have heard of them. They introduced, you know, laws which were very important to classify corpora, in particular the so-called vocabulary growth power law, which is still a problem for machine learning, and it is the increase in vocabulary size with respect to text size. Now, as you increase the text you're working on, then also the vocabulary will increase, and that will mean, you know, that new words will come in, and many of them will be out of vocabulary. I will talk about that later on. And then this important feature of the distribution of vocabulary in text, which is very skewed. Word types show a very long tail of words occurring very infrequently. This is what you find always. Corpora at the time they were very small compared to what people are using to nowadays. You know, no more than 1 million tokens, and the first one was an American one, the brown corpus that you see there. I think everybody in our field knows it. And then came the lob corpus, the European one in the 90s. What would linguists do in that time, you know, to describe what was called the stylistics, you know, the statistics in the stylistics of a text? You could use you know, distinction between token types, lemmata, the usual, you know, medium regression line. Then we'll be doing frequency counts, but also dispersion indexes, usage, absolute versus relative frequencies, and so on. But consider that, you know, nowadays, what is being used for machine translation in the sense of Dan, but in general for machine learning is still frequency count. That's the main measure. It's still there. To assess different styles, then the people were using, you know, the usual statistical test that everybody's using, even today, standard deviation, variance, you know, p-values, distribution, Gaussian and non-Gaussian. Then the collocations, which became more and more important, and even today they are called, you know, they're dealt with in specific conferences called multi-words. They become polywords or multi-words. Collocate simply, you know, the way in which you can study a token A and versus a token W, in case it is a collocate in a window at a given distance. So you measure that with association measure, which could be, be there a certain number of these measures, and then you can test the correlation. But then the most popular way to formalize the idea of a certain word, better, a certain term, to characterize a certain text was this this measure which comes from information retrieval, and but also from linguistics, because background was a linguist, and the TF-IDF family of weighting functions, you know. And this is very, it is very straightforward. You have the frequency in one text or document, and then you have the frequency all over the set of documents in the corpus, and you measure the two, and then here comes the inverse document frequency, which if it's low, it indicates a certain thing, and if it's high, the opposite. Generally, the word is important for that document. An alternative to that is the PMI, which works well in certain contexts. At a certain point, then comes probability. We are already around the end of the 80s, beginning of the 90s. I'm always referring to the fact that the majority of the researchers in the field started to take into account a certain approach rather than another. And probability became important around end of the 80s, even though everybody knows that the idea comes from Shannon's information theory, and Shannon wrote about it before the 50s. What people are using today is the Kalbach-Leibler divergence, the KLD, which is related to entropy, and this is related to the amount of surprise upon learning the structure of a part of or subpiece of language, and so that the predictability measure is used to weight words. That this can be used, you know, instead of the TF-IDF or together with that. And again, in the 80s, people already were using the Markov chain, but obviously this became more and more important because of the fundamental independence hypothesis. You know, the fact that in a chain of events, every future state has a condition of probability that depends only on the current state. This is very powerful because, you know, you don't have to look into many details. You just build up all the indices you need up to the current state, and then you can go on, you know. And the probability estimation is made on states and state transition. So background will be usually sufficient to compute predictability of a certain transition in a certain point of a text. And this was very powerful, in particular for automatic speech recognition. It has been used even up to some 10 years ago, say. It was really very powerful. And the fact is that, again, the probability is computed again through a frequentist or maximal likelihood estimation of discrete distribution. So we are still using frequency, count of frequency. The Bayesian approach introduces something additional, basically knowing what has happened in past events, the so-called prior. So the prior is computed together with the local probability in a given state. Again, this has been used by many linguists, and it is very effective. In particular, if you have a DAG or a direct acyclic graph, if you have a DAG to represent the dependence, you can represent causes, effects, symptoms, and diseases using edges and vertices. If there's no dependence between two variables, there will be no edge between the two vertices. Here, there's a seminal work of Anderson in 1990. This was in the cognitive field. So many people thought that the human language comprehension is also best modeled as a process of probabilistic Bayesian reasoning. This came really to become an important hypothesis when, as you will see in a while, a number of important linguists started using it. But here now I introduce another perspective, which is very important. So the difference between supervised and unsupervised approaches, where the unsupervised approaches, which are very dominant today, at least in the field of information retrieval and engineering and so-called artificial intelligence people, they would prefer sort of an empiricist approach. You learn from experience through the senses, and also languages learn simply by exposure, because human beings will be using a statistically driven process, which is again driven by exposure. There's nothing in the mind. They only will be using words and their frequency of occurrence. No abstract categories, nothing. Versus the supervised approaches, which in the case of language acquisition, it will be based on innateness, and innateness will be, they will be using principles, parameters. Of course, you need exposures just to tune these parameters, and then you will have also a learning mechanism, which will look into syntax first, and then introduce abstract categories. So there will be grammar rules and some mechanism. As I was saying, the Bayesian model was used a lot by human-centered processing. This is psycholinguists and linguists in general, where, as you see there, syntactic knowledge should be processed first, and then would more constraint would come to delimit the choices, the best candidates, whatever. Also, there are the online applications, so-called online applications, where all resources will be used together to constrain the interpretation by weights of some kind or other. And one of these linguists is David Jurafskis with the online model, produced eventually in 1996, as you see there. But then there's another example. Sorry, I will switch here, but you will have the PDF obviously available. There's another proposal by Crocker and Brents in 2000 that proposes a similar probabilistic model of sentence processing that uses cascaded Markov models instead of stochastic context-free grammars, and that will be made possible by statistical passing techniques invented by Brand. So this is still in the last century. As an important weight which would be used together with probabilities attached to the context-free grammar will be the fact that, again, frequency is important to distinguish high-frequency words from low-frequency words. Why? Because high-frequency words are processed more quickly than low-frequency words. I mean, in the mind, obviously. And so, in other words, this was tested by reading time, and reading time was shown to be inversely proportional to the probability of upcoming words. And here again, you have the surprise effect that we expect from the, Shannon and the entropy theory. Okay, so 2000, here comes the vector computation. It was already there, then it becomes important beginning of this century. And what does the vector space model say? A word may be represented by the elements which are derived from the occurrences of words in various contexts, using windows of words or grammatical dependencies or other richer contexts that can be used in order to define a word. The novelty introduced was to use frequency derived from a corpus of text as a clue to discover semantic information. This was the novelty and was very powerful, indeed, so that everybody started using it. One of the most important applications was LSA, the latent the semantic analysis introduced by Turney et al. In 2003, which introduced other important innovations. But it says basically if word pairs have similar row vectors in a pair pattern matrix, then they tend to have a similar semantic relay. This is more complex, and this will lead us to tensors. I will talk about it a little bit later on. So what has been the motivation for introducing vector space models? The motivation was already there, as I was saying, in the philosophy, in the philosophy of language. You see there Wittgenstein, Harris, Weaver, Firth. All these people are people of the 50s, you see, and they already said the same thing very much. That there are a statistical pattern of human word usage. Okay, so this is a very strong hypothesis, and I don't trust it very much. I'm sorry to say that, in the way in which it is being used today. I mean, I trust it, of course, but the way in which it is being used today, it is, it is being forced by the great quantity of data that are now being used. We're talking about billions of words to derive a model. But still, I mean, there are problems. Anyway, distribution of models is an important achievement in general, and vector space models are an important achievement. So from vectors, we go to matrices and higher order tensors, that is vectors of vectors. And this, they've been introduced, I would say, in the world of information retrieval by Salton et al. In 1975. How do people use these vector space model? The mathematics is very simple. It's taken from the measure of the cosine, so a geometrical measure. So they'll be using the inner product or the dot product of the two vectors, and then after they've been normalized and so on and so forth. I think everybody knows these things. Anyway, I'm saying these things because they will take me to further discussion. So there's people who assign distributional meaning to sentences using the Hilbert space tensor product. So here we're going into more complex models, and they're still being using nowadays in order to leave the deep neural network back somewhere, because it is too expensive in terms of material that you have to use in general, and trying to use a better model inspired by quantum mechanics. And this has also been explored in the world of deep semantics, like inferences and reasoning. Tensors are being used with triples that you see there, term document language. So in case you have a multilingual information system, or word and pattern, verb, subject, object. So three things together, with each one with a different vector and then together in a matrix. As I was saying, it has been used in logical calculus by these people, Widows, Van Reisberger, to show how disjunction, conjunction, and negation can be represented by vectors. And this comes from, first of all, the predicate calculus. Okay, so I'll have to move then to machine learning eventually, which is the final part of my presentation, and then to the doubts that come into mind in a person like me, a linguist who is both a linguist and a mathematician at the same time, but first of all, a linguist. So what happened at a certain point in time is that the increase in computer power and the memory size allowed the machine learning paradigm to become more and more important. So at the beginning, obviously, everything was already annotated. It was already annotated manually by people. So we're talking about supervised approaches. Obviously, this refueled the whole debate between generative linguistics and connectionism. This was going on in the 60s and the 70s, which in this case, people in the neural, in the deep neural models, they were claiming that you can represent synthetic information without explicitly encoding hierarchical structure. Connectionism was represented appropriately by Smolensky in 1990 with the famous paper called Tensor Product Variable Binding, the representation of symbolic structure in connectionist systems. And then there was obviously a system which uses a loss function, which is what is being used today, nowadays. What you have in a machine learning environment, you have the inference problem, which is formalized as generating the output, which can be a label or a set of real values, from a parameterizable function of the input, feature extracted from observations, while the learning problem consists in finding the parameters of the function that best generate the correct labeling of a corpus. And this is done as a loss function minimization problem that is directly minimizing the end task of the error. This method is introduced by Boser et al. In 1992. It has been used first of all by so-called support vector machines. Support vector machines are classifiers, basically classifiers when there's only two classes to distinguish. And the idea of learning is learning a linear hyperplane from the training set that separates positive examples from negative examples. And the hyperplane is located in the point of the hyperspace which maximizes the distance to the closest point, to the closest positive and negative examples, the so-called support vectors. So the problem would be to maximize the geometric margin between them. So what is going on here slowly is the passing from linear models to non-linear models like support vector machines, but also decision trees, which I didn't comment here, and then eventually neural networks. But as I was saying, neural networks are now the dominant approach, even though the BERT approach uses a new approach which is called transformers, which is something different again. Neural networks could also be called chain rule machines, which, however, use different layers. And as I was saying, its task is minimizing loss using parameters, weights. BERT, a few words about BERT, which has been introduced by Dan previously. It's the bi or bidirectional encoder representation from transformers. A transformer-based architecture is composed of several layers of attention introduced by Vaswani et al. 2017 that are used to learn a deep bidirectional forward-backward representation, which we had you build up a model of a sentence, as we were talking about a sentence, trying to capture as much as possible of the context. How you do that? Because people realized, that if you only do a forward chaining, you would lose a lot of the information that you had at the beginning. So then they started doing the backward. So you had forward and backward, trying to get the information on both sides. But then again, it wasn't sufficient. And so attention was introduced, which is a kind of self-supporting, reinforcing information from the surrounding context. However, this is my note down there, increasing the level of context sensitivity, reduces the way to generalize, which is only left to the so-called, the hypothesis that we had before, the distributional semantic hypothesis, which basically says that when two words share the same surroundings, then they also share the same meaning. But the surroundings are computed using frequency of occurrence of words. They're no longer there, the words. They're just their frequency of occurrence in the computation. Only numbers. You don't compute words, you compute their numbers associated with the frequency of occurrence in a certain context. Here a few words about machine translation. There's lots of resources. So this is the great invention made by a guy called Zampolli, who died some years ago, an Italian. He was a strong supporter of building language resources for language studies. Mm-hmm. And now there's a lot of these parallel corpora, or BTEX, from a lot of different languages, millions and millions of sentences. Of course, all these corpora, they belong to a certain domain, and this is really important. I will say something more in a while. So statistical methods began to be applied in the 90s and beginning of the 90s. Then came the IBM people. You see down there at the end of the 80s, publication by Brown et al. And there was a famous conference in Italy. It was a conference by NATO AC in Cetraro. This was in Calabria. And that in that conference, these people, the people from IBM, presented for the first time their model, the language model. So that started because these people, Brown et al., there was Jelinek between them. I don't know if you heard his name. Anyway, this was a great surprise, but then people were not so surprised because, everybody knew that IBM had a lot of money and they spent a lot of money in research. So, and then this worked. Then there was a toolkit called Giza in 2003, and then Moses that, generation of linguists have been using for machine translation. Okay, what is the deep neural network, any system made of? It is made of word embeddings. Word embeddings are compact vector representation of words that place words with the same properties close together for the so-called distributional semantic hypothesis that already quoted. This depends a lot on the way in which they have been trained, but of course, at the end, what you get there, you get the numbers related to the way in which words are organized in some semantic pattern, distributional semantic pattern. Nowadays, a typical corpus has 4 billion tokens, circa 4 billions. So you can imagine how much noise there will be in this corpus, because the quantity of noise that is there is, it cannot be deleted or erased or cleaned. There's a lot of work that is being done to improve them, but there's still a lot of noise in there. Anyway, as another important fact about word embeddings, and it is the dimensionality of the vectors. Usually a vector in these cases would be the dimension of the vocabulary. The vocabulary will be all the types that you find in a corpus. But in a 4 billion corpus, how big would be the dimension? 1 million, 2 millions? I don't know, just imagine these vectors made up of vectors of millions and millions of data that you have to compute every time in order to make up your model. This can be done in different ways, so I will skip this. But then, what are the main problems? Main problems are two, basically, the ability to generalize and the treatment of out-of-vocabulary words. For how large is your corpus, you will always be, you will always find out-of-vocabulary words. In other words, you will always find words which don't belong to your training corpus. So there's a way to measure the level of difficulty in the degree of generalization of the system. And this is what I found in a book by Guéron, which is, I think I agree. So the training corpus and the task corpus and the text you want to work on, they have to come from the same distribution. This is very important. Obviously, the only varying factor is the amount of data. Then, first difficulty would be coming from a different time frame, obviously, because the training data will come from, I don't know, 10 years ago, and the language will be the same. I'm not sure about that. So that's a first level, perhaps not so important. But then there's the fact that when you're collecting the text, you're collecting different genres, many times different language, also different language register, and also different modality. In some cases, you will find dialogues. and written text, but they're different. They're very different. And level 4, when the training deals with a different topic or a different specialty domain, medical versus sports, and you need something else. And then different language, even though this has been done today, multi-language computation is being done with positive results, but then you will need similar amount of data, and also different tasks depending on the task. So you will be using different important information. So devising representation for out-of-vocabulary words, that's one of the important things to do, even though the BERT framework is organized on the basis of the so-called closed test. But what's a closed test? For educational purposes, for second language learning, you leave one word out. In a text, you leave a number of words out. They're missing, and the student has to discover the missing word. And this is what is done in the BERT framework. Words are being masked. There's a masking being done. But to cope with out-of-vocabulary words, I don't know. Again, this is a problem, and there has been a number of experiments lately. I was in this conference on semantics somewhere in Amsterdam, and in fact, when you move from one domain to another, there's a big drop in the performance. But you see the words, out-of-vocabulary words can come from a lot of different places. Okay, I'm almost done. This is the final ideas about reasoning and inferential processes. Why am I introducing this topic? Because there are lots of people who really think that using deep DNN will allow us to understand human beings without any further processing. But I mean, even if you're using a text corpus which has been built appropriately, for the so-called syllogistic argument, you still would need propositional inference schemes, model schemes, argument schemes for practical reasoning, complex argument schemes with intermediary conclusion or assumption, and so on. And then always comes at the end the question that you would have a system that needs to discern contradictions and relations of logical independence. So this is something very interesting that has been discussed appropriately in a paper by Rachel in 1987. And who introduces these so-called aporetic clusters, which are well known by people in philosophy. And I have the important part of the article, which says basically that an apory is a collection of intentions that are indicated as plausible individually. But then if you put them collectively, they become inconsistent. And so, I mean, people still are inclined to accept things individually, but then if you put them together, you become puzzled. So computers, they will still continue to struggle with reasoning tasks. And this doesn't come as a surprise. Some people say, given the tendency of humans to commit errors in reasoning, and then to have sometimes limited critical thinking skills and finding, fallacies and biases. So I think I can end up by saying, you know, that the neural scheme, the neural network framework will not be the last one, and we are waiting to see more interesting language models, and but I think they need to be supervised. I don't know what's your opinion. Anyway, thank you.
Thank you very much, Rodolfo. These are, to me, are enlightening discussions of how to model language. And one follows from the other. Dr. Belenchik and then Rodolfo's really wonderfully done. Okay, the third topic is will be treated by Vitaly Kiryushenko at York University. If you've never heard of York University, it was started as a competitor to the University of Toronto in 1965. They accepted me, one of their first students, and I didn't go when I got a scholarship to go to the University of Toronto. Now it does not need to do it. It's one of the largest universities in Canada. And Vitaly is, I believe you're in the philosophy department, correct, Vitaly? Or one of the departments, anyhow. Today he will speak about if mathematics is a language, what exactly do mathematical statements say? Okay.
It is part of common sense to consider mathematics a language. The question is, and it's not, I'll try to show it's not a trivial question. It seems to be, what does it exactly mean to consider mathematics a language? You know, we can just resort to simple metaphors and say that mathematics is a language of nature, or we can choose to go circular and say that mathematics is a language used by mathematicians to communicate mathematical ideas among themselves, or something of the sorts. And we can try and introduce new variables and say that mathematics is a language of pure science, but then, you know, we need to explain why pure science needs such language in the first place. But I think that we can get slightly more interesting results if we pay attention to some internal characteristics of mathematics and mathematical reasoning that make it a language that is different from every other. And one of the examples is given in the philosophy of mathematics of Charles Sanders Peirce, American mathematician and a philosopher whose name you've heard in another presentation today. According to Peirce, mathematics is a special kind of diagrammatic language, and that's what's ultimately important. In fact, Peirce went as far as to claim that there's no mathematical reasoning whatsoever that is not diagrammatic. Even the purest of mathematics presupposes observation, and it presupposes experimentation with the visual imagery of some sort. And mathematical diagrams, Peirce says, are special in that they are visual signs that make the deductive force of reasoning immediately visually available, immediately visually given. That is, they are capable of leading us through a mathematical argument without using any other symbolic means. These diagrams are signs, Peirce says, that presuppose an immediate connection between how inferences in general work and the cognitive schematisms behind our ordinary visual perception. So what's important here that in the case of mathematical diagrams, the necessary character of deductive arguments is not simply illustrated by diagrams. So the diagrams are not just supplementary tools that we use for the sake of clarity. That the necessity, Peirce says, is internal to those diagrams. And if this is so, he believed that there should be something in the very way that the diagrams are constructed that conditions their deductive force. And from this, again, he believed that it follows that our visual experience at some basic level presupposes direct perception of necessary relations. And, you know, you don't have to look very far for example. Here are two examples that are simple to the point of, you know, being childish that, you know, I'll just give it to you for the sake of quick illustration. Here, you know, in both cases, we immediately see how points and shapes are related, and that the equations just repeat what can be immediately observed. So in this case, it's you know, it's a matter of two different ways of expression, and emphatically not a matter of one expression being simply an illustration of another. You know, yeah. So Immanuel Kant was first to formalize this connection between perception and mathematical truth. According to Kant, algebra and geometry are nothing but immediate expressions of the basic features of time and space. Mathematical intuitions, he says, never lie precisely because they are built into the very way we perceive. There's a mathematical a priori to human perception in general. That's why, you know, all these truths are always true. Furthermore, Kant took mathematical concepts to be very unique in one particular respect. On the one hand, what they represent, according to Kant, involves nothing empirical whatsoever. They're a priori notions. The idea of a number does not require images of particular things. Then the geometrical figure, you know, does not necessarily need actual representation in order to be understood as such. On the other hand, in proofs and theorems, a mathematical idea is always paired with singular representation. So mathematical ideas then are pure, but at the same time, they're also sensible. For instance, you know, the concept of a triangle, just like the purely empirical concept of a dog, is sensible since it is always constructed by a mathematician in concreto, so to speak, as having features that are common to several essentially similar objects. In other words, there are several kinds of triangles, just as there are several kinds of dogs. Yet, there's a difference between the two. Like a dog, a triangle is a particular object, but unlike a dog, it expresses a universal truth. So in the case of mathematics, according to Kant, what we have is a universal revealed through a particular or in a particular. And this is why, by the way, according to Kant, the beautiful, you know, it's a mathematical notion. It's also an aesthetic one, but it's an aesthetic notion only because it is a mathematical one. Because experiencing beauty is experiencing a universal harmony, not as exemplified by a particular thing, but as uniquely and properly embodied in this particular object. So again, we actually don't need a picture of a circle to have an idea of it. As such, it is based on not on visual images of concrete circles, but on a rule that exists only in thought. Knowing the relationship between radius and pi would suffice, and yet we have to use a particular picture in the mathematical proof, because the proof in this case is essentially nothing but a manipulation of particular images. And based on this simple observation, Kant makes the following conclusion. He says that in natural sciences, we begin with sensuous perceptions, and then we conceptualize based on those perceptions. what perceptions represent in this case is, so to speak, richer than their concepts. Concepts simply, predict what happens in general, and particular perceptions beget the nuances. To use a familiar example from one of Gregory Bateson's books, I can predict that a stone, if thrown at a window, would produce a crack in the glass in a star-shaped pattern, but within the conditions that produce the star-shaped break, it will be impossible for me to predict the pathways and the positions of the arms of the star. Conversely, in the case of metaphysics, a priori concepts are richer than individual tokens of their empirical usage, simply because this a priori concepts tell us something important about the very conditions of all possible experience. So in neither of the two cases is there compliance between concepts and the objects to which they refer. There's a disbalance between signify and signify, always. Mathematics, Kant says, constitutes a special case in that it mediates between science and metaphysics, in the sense that there's a special connection between ideas and their representations in mathematics. What is given in mathematical diagram is a general truth proven by means of a particular image. Again, it might seem that this is precisely what the words of any natural language, such as English, precisely do. In the case of mathematics, however, this image always happens to be in full compliance, as a Kantian term, in full compliance with the general truth it refers to, because being the particular image that it is directly visually translates certain general relations that are absolutely invariable. It does not depend on the size of a triangle or of a figure in question, or its particular characteristics. They always represent relations that cannot be varied. And this is something no image of any other kind, no word of any language can do. Now, if the force of necessary reasoning is immediately visually given in diagrams, according to Peirce, it should be possible to construct a deductive mathematical language that would amount to a complete system of diagrammatic expression only. The expression that is independent of formal symbolic proofs, a purely diagrammatic language that would express necessity visually by using the most basic features of and our orientation in space and time. So we need to invoke some basic bodily experience in order to understand what the mathematical diagrams are. And what is meant by this will follow shortly. A version of such language is actually introduced by Peirce under the name existential graphs. Existential graphs consist of three parts that Peirce called alpha, beta, and gamma. And these three parts roughly correspond to what is currently known as sentential logic, predicate calculus, and modal logic. And reading Peirce, we can distill three conditions that make such visual language possible. Condition number one says that diagrams should represent an independent language that can be mapped on what our ordinary visual experience presents to us as reality. In the same sense that, a function maps the elements of one set onto the elements of another set. That sounds a bit cryptic, but there's a good and I think very illustrative example, which is suggestive illustration of this idea that may be found in Ron Howard's movie, A Beautiful Mind, with Russell Crowe playing genius mathematician and the Nobel laureate, John Nash. And here's two very short videos, like less than 1 minute for you. And while you're watching, it's important to kind of take note how Nash writes his formulas and what he writes them on. So take a look.
Well, it's official. I'm almost human again. Officer, I saw the driver hit me. His name was Johnny Walker. You've been in here for 2 days.
You know, Hanson's just published another paper. I can't even find a topic for my doctorate.
Well, on the bright side, you've invented window art.
This is a group playing touch football. This is a cluster of pigeons fighting over breadcrumbs. And this here is a woman who's chasing a man who stole her purse.
Okay, so just a second. Oh, just 1 second. Or something. Could you hear? Okay. Okay.
Yeah.
Good. So Nash is in his dorm. In his dorm room at Princeton, looking through the window, right, at his friends playing football in the yard. He grasps the pattern that describes the way the game goes and begins to cover the window glass with formulas. So a mathematician makes a leap from images, what's out there in reality, to formulas by mapping one onto another. He needs this mapping. Window glass becomes an ideal transparent medium for this mapping. And for Nash, the formal symbolism and vision are immediately connected, one map onto another. They're two sides of one sheet of paper. They're inseparable. There is a cognitive mapping rule that immediately translates pictures into mathematical symbols and back. What a mathematician sees in this case is a pattern, which is a relational picture, a diagram. And a set of such diagrams constitute a language based on the way we orient ourselves in space and time. And again, what is meant by this will become clear very, very shortly. Now, the second condition is that basic visual intuitions that we have are to be considered as immediate expressions of our logical and mathematical capacity, which for Peirce meant that we should be capable of applying basic intuitive spatial relations in order to express logical connectives. And here's a few examples of the most basic conventions of alpha and beta parts of Peirce's existential graphs. So the convention number one is called a cut. Cut signifies negation. So when we negate something, we don't want to see it. We literally, what we need to do is we need to cut it out of our visual field, cut it out of what Peirce called the sheet of assertions. We don't want it. It's out. The second convention is two objects situated in close proximity to one another. You know, naturally, when we see two objects together, we perceive them together, and the sense of togetherness means and or, you know, conjunction. Convention number 3. So this basically means if this means A and B, this means not A and B, this means A and not B, and this means it's not the case that A and not B. And what's interesting is that this is already an implication, right? Yeah, and again, if we put another negation here, if it's not the case that neither A or B, it immediately means that either A or B, so it involves disjunction. So what's interesting about this system, as simple as it looks in the beginning, it uses a very few basic ways to orient ourselves in space, to express what we basically have is 2 perceptual intuitions to express 4 basic logical connections. Again, the sense of togetherness and negation as cutting out is enough to express negation, conjunction, disjunction, and implication. Now, the third element that Peirce uses that is called the line of identity. I'll keep that. Line of identity. So the line of identity is called the line of identity because it establishes the identity of something that exists. And the line of identity serves as a transition for Peirce from sentential logic to the predicate calculus, because by using this line, we acquired capacity to express predicates. So we may say that there is something that exists, and this something is ugly. We can then use the negation and say there's something that's not ugly. And then we can use another negation and say that it's not the case that there's something that is ugly, which immediately means that everything is ugly. So again, using this 2 basic perceptual intuitions and adding another one, which is just a simple sense of 2 things being connected by a line or a rope or whatever. We express now not only 4 basic logical connections, connectives, but we also express 2 quantifiers, an existential quantifier and a universal quantifier. We are now capable, to quantify statements simply, again, by introducing this line, which is, which makes this system a very intuitive and very, very kind of elegant and economical. Now, condition number 3 says that according to Peirce's analysis, the diagrams should move. We should be able not just use our basic spatial intuitions, we should be able to move the diagrams to show how the spatial intuitions reveal logical and mathematical truths. The question is why, Peirce insists that diagrams should move. He says that the system of graphic conventions should be supplemented with a corresponding system of moves. Because our visual recognition works best if objects at which our attention aims at, if these objects move. And it is just as true of ordinary perception of, mid-sized objects like tables and persons and beds and trees and stuff like that, as it is true if our object is thinking itself, right? And again, here is a simple illustration of how this moves work. There's an A, and the A exists. And now we're saying that some A's are B's. Some A's are not B's. It's not the case that some A's are not B's, which means that all A's are B's. Now, if we want to move from this picture, if we want to use this picture in order to illustrate, I don't know, some simple Aristotelian syllogisms, such as Barbara, we need to do the following. We need to create a statement in a similar manner that says all C's are A's, right? Now we need to prove that all C's are B's, right? So we enlarge this picture. We put the first one into the second one. We connect the lines of identity. We delete two elements that are the same. We delete double negation. We simplify the lines of identity. There we go. We have this conclusion. Let me demonstrate it again. So again, there's an A. Some A's are B's, some A's are not B's. Now we universalize the statement. In a similar manner, we say that we create another universal statement, and now we just put one into another and delete all the unnecessary elements and simplify all the connections. So this is all we have in order to demonstrate how Barbara syllogism works. So now, if mathematics is a language, what exactly do mathematical statements say? Some say that mathematical truths can be known by thought alone and are true no matter what happens. But if the statements of mathematics could not be false no matter what happens, how can they actually tell us anything about what happens? And if they tell us nothing as to what happens, how can they help us in any everyday scientific inquiry into what happens? And these simple questions show that, you know, if the simple universalist claims obviously lead to nowhere, but if we have a closer look at what mathematics actually does, how it experiments with our assumptions about what we perceive and how we orient ourselves in space and time, we might actually have some progress in answering this question. And with this, I stop my presentation. Thank you.
Thank you so much, Vitaly. I always learn from you about PERS, always, all the time. Thank you, and thank you to everyone. So we have about 20 minutes for discussion, if one should emerge. So I open it out to whoever wants to ask any question of the four speakers, including some of the speakers themselves asking other speakers. Can I ask a question? And I'm going to ask one of Vitaly. The idea of existential graph can be expanded clearly, because would you say that an equation is the result of the third level of existential graphic thinking or not?
What do you mean by like a
simple equation? Any equation, yeah.
Well, first of all, according to PERS, any mathematical equation is an iconic sign that shows how two kinds of relations work together. it is an iconic sign proper because it shows not how two objects are similar with one another. It shows a similarity between relations. So I'm not sure about the levels, but you know, the equation is a diagram.
Yeah, but is it an existential graph?
No. I wouldn't, you know, I might be wrong, but I wouldn't say so because for Peirce, existential graphs is a special kind of language that exemplifies an appeal, a very particular appeal to vision that basically shows that thoughts as objects are no different from any other object if we want to study them, and when we begin to study them, we find many analogies between how our ordinary perception works and how mathematical truths can be expressed. But to call an equation an existential graph is to include it in the system that uses only a certain particular set of spatial intuitions. It appeals to very few basic ways we orient ourselves in space and compare things. And yeah, so how mathematical equation as such can be fit into this, I don't know. Maybe it can, but maybe you know, there are other people who know better. So
yeah. I'll tell you why.
May I offer my insight on that?
Yes, please.
May I ask you a question?
Okay, problem is that when you write down an equation, now let me use, I mean, I'm not an expert of those things, so let me use my language. And when you write down an equation, you do not assume that the equation has a solution. When you write down x squared equals 2, you don't assume that there is an element whose square is 2. It's just a template for reasoning. Then if you say exists an x such that x squared equals 2, then you get into all kind of arguments, because I mean, it really depends on where you are, right? And in this sense, I mean, it's not, it has nothing to do with the existentiality, in my opinion, writing down an equation. It's just a template for reasoning. I don't know how to frame it in this theory, but
just a brief note. Peirce calls his graph existential in a very simple sense that when you put this graph on the sheet of assertions, it immediately refers to the existence. It exists, and that's all there is there. You know, that's why these graphs are existential.
Yeah. I mean, so if you say x squared equals 2, you must be able to show me an x squared equals 2. Yes. That's the idea.
Yeah.
Yeah. Okay. There is another, yes.
Yeah. May I ask a question? It's rather a remark. My Chinese friends often try to explain to me how the Chinese children and themselves, how they learn to read. And they explained to me that roughly what you explained, that they grasp immediately the topological and geometrical sense of the idea without going through words.
Yes.
The Chinese writing is mathematical writing in a sense, as you described.
I think you're totally right. And I was told by numerous people, by Peirce scholars, who told me that Chinese people in general understand Peirce's triadic logic, logic that's not binary, you know, much better than Europeans, actually.
Yeah, but the point is that, you see, the problem with this way of learning is that you have to do it when you are a child.
Yeah,
exactly.
Yeah.
Because
right,
I mean, if you are grown up, the only way to learn Chinese is rote memorization, and that can be very, very
It's very hard when you are.
Yeah, because I mean, you totally lose this capability of. Which brings me to a question I wanted to ask.
There was a discussion. There was a discussion, another one, that said that the people who learn early this Chinese writing, the ideograms, they have some better understanding of geometrical and even space relationships.
Well, that would
be. Then there is another idea that says that maybe it is there is something genetic, that the people who were able to invent such thing were already better in grasping things. Like
I wouldn't vouch for the second one, because I mean it's dangerous. But for the first, I'm sure it's true, because I mean, if you deal with shapes and forms and things since your childhood, I mean that's only normal that you're better in handling them when you're a grown up. I mean, it's just normal education.
Yeah, but somehow this kind of thing did not catch in Europe, for example. We opted for
okay. It's I mean that's we have to delve deeply into linguistics, and I don't know if I'm prepared enough.
May I say a word as a linguist?
Okay.
There's another important aspect, and it is the fact that children that don't learn one sign every day, in the evening they are beaten. As a linguist, the parents are very strict. They're very strict. They work together with the school, and they are obliged to learn. They're not just learning as we do in our countries, democratic countries. And of course, that makes the difference, I think, because children have to learn a certain level of Chinese in a very quick time, which is, I mean, for other people, it will be 4 or 5 years. Chinese is being taught here in Venice, and it takes 4 years, but then you need to go to China if you want to start reading, the first page of the
newspaper. They told me that in order to read really some more complicated literature,
but also to understand.
9 years learning.
Sure, but also to understand and to speak a little bit, again, it takes 2 or 3 years, depending on, the way you're able to do that. But there are 2 aspects important here. And one is the fact that they read from one verse to the other, which is the opposite of what we do. So, I mean, they start reading at the end, and then they continue backwards. And this makes a difference in the brain. They will always start looking at things from the other side compared with us. We will start looking at things from the left to the right. But, all languages...
No, not everybody. No, not the Arabs, no, not the Hebrews. No, that's not true.
No. This is based on experiments. People who are used to write from the left to the right. They look at things differently from people who are used to write from right to left. Totally different. And then there's another important thing, the fact that Chinese language, as the majority of words are monosyllabic. They're monosyllabic. So, I mean, this is also apparent in languages like English, for instance. There's lots of monosyllabic words, but Chinese words are monosyllabic, and they contain content words, not just function words.
Yeah, but they contain 4 different tones. There are 4 different tones, which makes another parameter.
Sure. But then, you need, of course, you need to learn tones, and that's an additional part, obviously, of the difficulty level. Then it doesn't have to do with writing, obviously, but it has got to do with understanding, obviously. Certainly, as you were saying, the geometrical part is certainly very important in the language learning phase, because then there's the maturation. Language maturation is important, and it works differently, certainly from a period of language maturation, children age 5 in China, they would not have the same ability to, to understand as we do as children in our countries.
Yeah, but when they look at the written text, they understand the concepts already without going through how it is pronounced. You can have a Japanese who knows Kenji, and he will understand the same thing.
Sure. But this is
different.
This is due to the fact, that ideograms they contain no ambiguity. This is very important. They're no longer semantically ambiguous. Where on the contrary, we have a lot of ambiguities. Yeah, sure. Yeah, you're right. Sure.
Just a bit of information in the series that I edit, Mathematics, Mind in Mathematics. We have a book forthcoming by a physicist in Toronto, Bob Logan, who was also a student of McLuhan, as I was. We were contemporaries, on the origins of writing and mathematics, pictography and mathematics, and therefore diagram and thought. It is a brilliant book, and it connects a lot of these ideas here, because all writing, all of it, starts as pictography, as iconic signs. It just develops into alphabets when we start using them a little more abstractly. Like, I don't want to go into it. I mean, this is well known.
Well, but I mean, the Greeks didn't have any proper way of representing numbers.
No, but the Greeks took the alpha, the alpha, and turned it into the alpha, and that became also the number 1. So this book shows brilliantly how the two are connected, and that is one of the goals, one of my goals anyhow, in founding the center at the Fields, to show how these things are connected. Mathematicians know it, and that's why I came back to the idea of equation as part of not only an iconic system, but a graphic system that could not have ever emerged without this kind of thinking. Anyhow, sorry, I don't want to intervene.
No, I mean, I have some observation on your talk, Marcel, if I may.
Yes, please.
Okay, first let me stress that, I mean, here I've discovered the truth of the 6th degree of separation, because I mean, first, we have discovered before when we are talking in Italian that my late mother and Marcel were colleagues in Siena in the 80s.
Yes, absolutely.
So, and then there is the other thing that it's coincidence that, my first cousin, Margarita, she's a professor emerita in York University in Toronto.
Really?
Yeah.
Really?
Yeah.
I didn't know that. In what field?
Spanish literature.
Spanish. Okay.
Glendon, in Glendon. She's in Glendon.
Oh yeah.
Margarita Feliciano. She changed her name, but
okay, then the name rings a bell as well.
Yeah. She's quite famous in Toronto.
Yeah.
So.
Yes.
Okay.
So this is
but I mean, the question was, okay, you said that the ability to count is sort of innate or native, and I would maintain that this is not exactly correct, because I have an experiment, right? Because I'm a scientist and I have an experiment. And this is an experiment I did with my 3 years old daughter many years ago. And before you ask, I mean, she survived it, and now she's a registered nurse, so she's working, so she's fine. And that was the experiment, right? I mean, my idea was, okay, the very young children, they do not understand ordinals, so they do not understand really counting. But they do understand cardinals, so they understand quantities very early.
Yeah.
And that's the experiment. Okay, first you have to find a child who likes candies, and this is not hard, in my opinion. I mean, almost every child likes candies. And then, okay, I proposed her two different bunch of candies, right? And I said, pick one. You can eat one. And she immediately picked the larger one, without even thinking. Now, what the second part of the experiment? You take the same amount of candies and you put in a paper bag 1 by 1 in front of her. And then you tell them, which paper bag do you want? And she's not able to decide which one is more preferable. She chooses randomly. And I did it, at the time, I mean, a 3-year-old, I mean, you can have her do the same thing for a long time. So I did it. I repeated the experiment. And so, I mean, it is more like perceiving quantities that is innate in the human being, in my opinion.
No, absolutely. And in fact, it's consistent with the research of Jean Piaget, who
Yeah.
would do a lot of this kind of research and going from concrete operations to abstract ones.
Yeah.
What I meant by counting is also something that, you know, Dehaene and Butterworth call numerosity. Numerosity as an innate trait. I'm not sure it is innate, but numerosity, the ability to distinguish between one and more.
Yes, and that's not the ordinal, that's the cardinal. That's exactly what I'm saying.
Exactly. Oh, no, ordinals are indexes, and these, if you look at development, and I've actually been involved in it, the development of language as well. This is an indexical phase. That comes after iconicity. That comes after things that are resembling.
So we are actually saying the same thing with different
the same
words.
thing. Yes. Yeah.
Okay.
Thank you for concluding. By the way, I should tell you that I miss Siena. I used to come often, and I will never come again because I have a terror of flying.
Yes.
No matter how many times doing.
Well, you can take a ship.
Oh, sure, and I'll be there next year.
No, it takes 8 days. I mean, it doesn't take so long.
Lasciamo perdere.
Anyhow.
You take a ship, you can come to Venice directly.
Yes.
My grandchildren are dying for me to do this because they absolutely adore Italy. They are, who doesn't, right? Listen, I don't want to promote Italy to the non-Italians, but my mind thinks that way. Okay, one more comment before.
Okay, I do have another observation.
Oh yes, please, yes. Okay.
On Dan Bielenchik talk.
Yes.
And I mean, the thing that I mean, I don't know, but you know, he's too young probably, but you know, you know, Star Trek, right? Star Trek, they're famous, right? Maybe Dan is a little bit too young to be a fan, but I mean, we older people, we are fan of Star Trek. Yeah. And there is in Star Trek, there is this universal translator, right? So everybody can understand each other. Yeah. And I mean, the way this universal translator is supposed to work, because I mean, you know, there is a famous book called The Physics of Star Trek, in which they explained, right, what is it's not so different from what Dan was proposing.
No, you're right. You're right. I never thought of it, but you're right. Yeah.
And that's interesting because I mean, it is not the first time that science fiction precedes reality, right? Because
without going into Star Trek, also apparently the inventor of the cell phone was inspired by
but there is the famous thing, you know what a Waldo is. A Waldo is that contraption that you know you put your hands into the gloves and you work.
Yeah, into that.
Yeah. And that is described in a short story by Robert Heinlein in 1941. So
we're beginning to reveal our age, carissimo Agliano.
Well, I mean, I'm younger than you.
One comment about the idea of how writing affects cognition and development of language, which brings us into the idea of the Whorfian or Humboldtian hypothesis. Which is a very fascinating one to this day. If you look, and I've been looking at emoji writing, which has been introduced into, you know, the alphabetic writing system of in the informal register, and experiments from it. And I'm starting to become involved in with other people. I mean, although I'm getting old, I get other people to do it and then I intervene for the analysis. That the Western mind, the one that uses, that's been reading for 500 years since the, revolution in typesetting, is starting to change and view things differently. Two reactions I've noticed. We're losing it. We're becoming less and less reasoning creatures. And the other one, well, we're going back to the visual origins of pictography. I actually gave a TED talk on this, which is still available on the internet. I do really believe that I think it was Kerner who pointed it out here, that exposure to visuality, which we do anyhow in Western cultures by showing illustrations while we read to children, is becoming more and more incorporated in how we think and we are retrieving, as McLuhan would have said, that iconic visuality of the past that we lost when alphabets kind of obscured it. So we are retrieving it. It's a cycle that goes on forth and forth. And that discussion was fascinating between the people involved in that discussion. And really, I welcome people to continue working with us. And if you do want to be part of it, please write me an email. I would love to include you in our fields, in our cognitive science network, so that this discussion can be carried out more formally.
Marcel, sorry, but it looks like that people at Google have already heard about you, because they invented now a new system called MAM, multitask, you know, universal, whatever, which uses images and text at the same time.
Yes. I mean, if we might add a historical note, I mean, maybe you don't know that for sure, but I mean, in the early part of the 1900s, it was considered very bad taste in mathematics to write papers containing figures, pictures. It was considered very bad taste because, I mean, it was something, you know, mathematics had to be pure symbolism. Pure symbolism. Now, I have to say that one of the pioneers of the reintroduction of pictures that now we use profusely in you know, any one of my papers contains at least 7 pictures, okay, that we use profusely now, is an American mathematician. He was in lattice theory called Dilworth. Dilworth, Peter Dilworth. He actually forced people to publish his papers with pictures and with pictures with different colors. That at the time was a task. But you know, to capture 3-dimensionality, you know, you had to use different colors and that's a very interesting historical note, because I mean, in fact, if you read early 1900 mathematics is almost ununderstandable for us. I mean, it's sometimes it's really, I mean, of course it's correct mostly, but it reads like gibberish. Nobody writes that way anymore, and I mean, that is because we reintroduced pictures now in the. But if you look at papers, I mean, from the late 1800, early 1900, I mean, you see pages and pages and pages of symbols without a single picture.
In physics, the revolution came from Feynman. Introduced Feynman diagrams, and this is the writing, instead of writing complicated integrals, you symbolize what the particles, how they interact, and this has this
Feynman was good at many things, and he was also very good in appropriating, you know, in becoming famous for things that other people did. But I mean, that's just
no.
Yeah, well,
he did a lot by himself.
Yeah, oh, of course he did. Of course he did.
Okay, maybe one more question, and then we stop, and we can continue. Honestly, as I said, in other ways, this is fascinating. Anyhow,
it doesn't happen very often. I mean, as a mathematician, I always talk about mathematics. I mean, you know, hardcore mathematics. So having a more humanistic discussion isn't that bad. I mean.
Okay. One more. Vitali, you had a question?
It's just a comment. So if anyone has a question, I'll just, you know, shut up.
No, please.
I have a question.
Okay, so sorry. Okay, so the comment is this. When we, from my perspective, from my personal perspective, when we talk about visuality, and mathematical visuality, there's one important distinction that we have to make, and it's important to understand what this mathematical visuality involves. When we learn language, we in order to learn how to call things, how to assign colors, so to say this is red, this is green, we have to make a lot of attempts at a lot of exercise when we're little children. We in order to be able to say this is red, we have to know a lot of things that red lollipops taste like cherry, that red color signifies communism, that we have to know something about traffic systems. So in order to form an abstract concept of a particular color, we have to have a lot of inferential links at hand already. So in this case, in case of language learning, inferential connections, inferences precede vision. They form it. That's the way I see it.
Yeah.
In terms of mathematics, in case of mathematics, this picture is reverted. We use visuality in order to illustrate, in order to embody inferences. It's the opposite.
Yeah.
I mean,
Very good. I never thought of that, Vitali. That's a good point.
Yeah.
Very good point. Yeah.
Yeah,
Okay,
I mean, everybody looks at things from his point of view, of course. I mean, we are human, right?
Okay, Norbert.
Yeah.
Maybe?
Can you revert back to the notion of practical logics?
Yes. Again, this is it's my interpretation of PERS, because as many semioticians as there are interpreters of PERS. But it's the practical logic, basically, or utens, is the kind of idea that when, if I'm not mistaken, in a book by Serbia, Eco and another person, the sign of three is when you are in a crime scene, you see things together and your practical, how do they fit in together? That's the basic question. If you have a learned logic, if you've done it many times, then you can use that and map it onto that, and vice versa. A learned logic, you learn how to reason, because reasoning, and this is appealing to me because with Giambattista Vico, for him, rationality, reasoning has to be learned in every single generation. Practical logic, intuitive, does not. That is part of who we are. So going from one to the other is a sign system in the middle. And the sign system is a triadic one, where the interpretant comes into play. It's a little complex, but to summarize, when I teach a student, and Socrates did it as well, if you teach a student mathematics, you assume that they have a certain practical knowledge of how things work, how they fit together. What you do is take that, and it becomes a learned knowledge by systematizing it, organizing it, and then can be used to understand that practical intuition that you had before. Utens versus docens. Useful versus a learned logic.
Okay, again, may I offer an example that
yes.
can simplify things a little bit? Okay, let me show you one thing. Okay, this is the way I was exposed to mathematics first. This is an Italian book, which contains a lot of problems like the one Marcel mentioned. I mean, the wolf, the cabbage, and whatever, right? And the Ozymandias problems and all these kinds of things. Of course, I was maybe 13 or 14 when I started reading this. I didn't understand, let's say, 80% of it. But the 20% I did understand, it was this kind of practical logic. I mean, the one that you use to solve problems.
The river crossing problem, yeah.
Yeah, the river crossing problem. Then when I became a mathematician, on going from a totally different direction, I sort of remembered after a while this, right?
Yeah.
So that's exactly the difference between the...
Exactly, yeah. Yeah, thank you. That's exactly the difference, yeah. And that's what I meant at the end of my talk, that these popularizing books are probably as important as technical books, because they may allow you to, there is an interaction between the two of them. And after all, Courant was a very famous mathematician who understood this more perhaps from his own point of view. And Robbins as well, right? Yeah.
Okay.
Okay. Thank you, Melania. Thank you for the session. And thank you, everybody, for having been here.
Thank you, Melania. Thank you for your work. Thank you.
Yeah.
Thank you very much for your your acceptance to be with us during this conference. Thank you very much for our today's presenters. Thank you very much to Marcel, who accepted to be organizer of this nice colloquium, which initiated so, how to say, so fruitful and interesting discussion. Believe me or not, we are not in hurry now. So let me remember you that tomorrow we will start at 9:30. Please, please check conference program. Although we don't have any change for tomorrow's session, for tomorrow conference day, there is one difference when comparing with the starting hour today and on Wednesday. Only for tomorrow we will start at 9:30. And prepare yourself. We will have a conference dinner tomorrow evening.
Okay.
We are in all.
So careful, because tomorrow afternoon is hardcore logic. So it's
after this colloquium, we will go somewhere. Not somewhere, in a certain place. So we can bring our computers.
I'm sorry not to be able to be there.
No. It is during the Corona time, there are new habits appear in Serbia. So we invite our friends on the dinner, and then we start with Zoom or Teams. We are with our meals. Our friends are there in their homes with their meals. So from that point of view, we also can share dinners.
Okay. Bye-bye, everybody.
Okay, thank you very much. See you tomorrow.
Prehistory, Antique Nisus, the Crusades, the Ottoman occupation, World War I and World War II. Experience the history of the entire Europe in one city.